Okay, last time we finished when dealt with indicator functions. So do you remember what an indicator function is? What is indicator function for the set A, which is a subset of some fixed x? What does it mean? The indicator function of A. It is a function where from? From x
where is
to
the set of two elements. So, and this function is defined the following way. Its value is 1 if n is an element of A.
And if 0 is n is not in A.
Of course, and it's 0 otherwise. Okay, and what do we know about these indicator functions? The indicator functions provide a bijection between the set of all subsets and the set of all functions from x to 2. Do you remember that?
Yes.
So all functions with values 0 or 1 comprise the same comprise this set, which is equivalent to the set of all subsets. So this bijection is quite clear. To each A you map to its indicator function, where of course A is a subset of x. Okay, and now let's move further. So let's recall what does it mean 2 underlined to the power 3. Now we interpret it not as the set of functions, but as a Cartesian power. What does it mean? Say a squared without underline sign is what? Is a times a, the set of all possible ordered pairs of the elements of A. Is it clear?
Yes.
And what is 2 to the power 3? By definition.
The set of order pair is E, Y, yes.
It is a set of all ordered tuples, ordered triplets. So x, y, z, where all these numbers are taken from 2 underlined. Is it clear? It is just a set of all ordered triplets, much like, say, r cubed is identified with a set of all points of the space via coordinates. So x, y, z are coordinates of some point. Is it clear?
Yes.
And now let's explicitly list all the elements of this set. Which triplets are there? Let's name them all explicitly.
0, 0, 0.
0 and 1.
What else? 0, 1, but it should be a triplet. 0, 1.
2. No, 0, 0.
What else?
1, 0, 0.
What else?
0, 0, 1.
0, 1, 1.
0, 1, 1.
1, 0, 1,
1, 0, 1.
1, 1, 0, and 1, 1, 1.
So, how many
8.
do we have? 8 triplets. And there is no coincidence that 2 to the power 3 is exactly 8. It's quite clear to understand that there is exactly 8 such pairs, for you have 2 ways to choose the first coordinate of the triplet, and for every such way, exactly 2 ways to choose the second coordinate, and for every such way, for every way to choose the first 2 coordinates, you still have 2 ways to choose the third one. So 2 multiplied by 2 multiplied by 2. This is the informal proof that we have exactly 8 of them. But let's not focus on these ideas, but rather compare this set with some other one. 2 underlined to the power 3 underlined. What is it? According to our definition, y to the power x is what?
Set up all functions from x to y.
It is a set of all functions from x to y. So that means that this one is just the set of all functions. Of course, formally, I have to specify where these functions are taken from. So all functions from 3 underlined to 2 underlined. But can you name them explicitly, these functions? What is a function? Every function is a subset of this binary, of this Cartesian product. So every function is a binary relation, some set of pairs. Can you name these functions explicitly? For example, every function is of the following form. There are exactly 3 pairs. So this is so every function has the following form: 0, the value at 0, 1, the value at 1, 2, the value at 2. Is it clear?
Yes.
So any function is of the following form. So can we explicitly list all these functions?
Yes.
So please.
0, 0, 1, 0, 2, 0.
0, 0, 1, 0, 2, 0. So this is a function which takes 0 at every argument. What else?
0, 1, 1, 1, 2, 1.
0, 1, 1, 1, 2, 1. Another constant. Another function which takes the same value everywhere. So next.
0, 0, 1, 0, 2, 1.
So, and how many functions do we have?
8.
8. But why is it so? So 8 functions and 8 triplets. But does there exist any natural correspondence between triplets and functions? Of course there is. Let's have a look at this triplet. 0, 0, 0. we may think that this triplet somehow encodes our first function. Why? We can interpret our first coordinate as the value at 0, our second coordinate is the value at 1, and the third coordinate is the value at 2. Is it clear?
Yes.
So, which triplet is encoded by this function, 1, 1, 1?
The last.
Clearly the last one. Mhm.
Sorry, I couldn't follow. I didn't understand. Could you please repeat what you said from the red one?
So, the main idea is that we can somehow encode our functions with triplets and vice versa. Just look, if we consider only second coordinates of our pairs, only function values, these values comprise an ordered triplet. For example, if we consider this one, this function corresponds to which triplet?
0, 0, 1.
0, 0, 1. And vice versa. Assume that we have some triplet. Can we construct a function?
0,
Right.
1, 0, 0, and
We may think that this triplet encodes the following functions: 0, 1. So
One
the
bit.
first coordinate means the value at 0. 1, 0, and 2,
1.
of course. So we may continue this way and see that there is a bijection, one-to-one correspondence between these two sets. Is it clear?
Yes.
So that means that our powers, whether with the underlined exponent or without underlining in the exponent, they are essentially the same. They are equivalent. Let's go abstract and state and prove the formal theorem about these things. So for every set A, this theorem is very easy, yet it is quite useful in practice. For every A, for every natural number n, the set of all functions from n underlined to A is equivalent to the set of all n tuples. Okay, let's prove it. My proof will not be very rigorous, but quite enough for our current purposes. Okay, let's prove it. So let's consider some cases. What if n equals 0? When n equals 0, n underlined is what? What is the set of all naturals which are less than
Empty
0?
set.
The empty set, of course. Hence, our a to the power 0 underlined, a to the power empty set, it is the set of all functions from the empty set to a. We have already computed this set. What is it?
Singleton of empty.
So the empty set is the only function from the empty set to a. Ha! And what is a to the power 0? Let's recall the definition to our minds. So a to the power 0, it is just that. Why? By definition. So they are equal, and of course then they are equivalent if they are equal. Is it clear?
Yes.
The second case. What if n equals 1? A to the power 1 underlined. First of all, what is 1 underlined? The set of all naturals which are less than 1. Which naturals are less than 1?
0.
That's 0. And only 0. So here we have the set of all functions from this one element set from this singleton to A. But what can you say about any such function? What is a function from the empty set to A? What does it mean that f is a function from this set to A? What does it mean? F equals what? Every function is a set of pairs, argument value. What is the only, so for argument, how many pairs do we have here in F?
1 pair.
Surely, exactly one pair, but which one?
0.
0, and the second coordinate is what? Whatever element of our set A. Is it clear?
Yes.
So, this set is just the set of such singletons. But how many such sets do we have? How many? As many as?
A.
As many as we have elements of A. So this set is clearly equivalent to the set A. So the bijection is of the following form. You map this set to A. So these two are equivalent, we have a bijection. And by definition, this set is just 1 to the A to the power 1. Is it clear?
Yes.
So, and the only remaining case is when our n is at least 2. So what if n is at least 2? Okay. So our n underlined is a set of all numbers that is 0, 1, and minus 1. Do you agree?
Yes.
So what do we need? We need a bijection. We need a bijection phi from the set of all functions, from the set of all functions to the set of all tuples. So we need a bijection. We want this phi to be bijective. Okay. Assume that we are given with some function. Let's define this phi. Phi of f must be a tuple. Which tuple it's natural here to take? Which tuple?
F0, F1, up to Fn minus 1.
Of course. Of course. What else? So let's take exactly this tuple. And here lies some laxity of my presentation. What does it mean? That we define the function by this equation. Here, it's needed here some form of recursion. But anyway, I think that informally it is quite clear that such phi can be defined this way. Is it clear? Intuitively. The tuple of all the values of f. Is it clear?
Yes.
So let's check that phi is indeed a bijection. So why it is injective? Why it is injective? So let's check it. Assume that phi of f equals phi of g. With this assumed, we have that these two tuples are equal. But we have had a tuple equality criterion. What does it mean? That two tuples are equal. When two tuples are equal, when two pairs are equal. XY equals AB when?
S equals A, Y is equal B.
Of course. And you know what is a tuple? Say a triplet is such a pair by definition. So when two tuples are equal, dear students, when two tuples are equal?
When all elements of tuple are equal.
So when their respective coordinates are equal. So that means that f of 0, the first coordinates, are equal. And so on. The every respective coordinates are equal. Do you agree?
Yes.
But we know that f and g are functions on the set of 0, 1, and so on up to n minus 1. So our two functions are equal when? So formally here we use tuple equality criterion. And here we shall use function equality criterion. Function equality criterion. When two functions are equal,
if they have the same domain and the value of
their values at every point are the same, of course, are equal. And here we have such situations, their values are equal at every point. So what does it mean? That means that f equals g, or doesn't it? Is it clear?
Yeah.
So if phi of f equals phi of g, then f equals g. And another statement that phi is surjective. Phi is surjective. Let's recall that phi is from the set of all functions to the set of all tuples. So I am given with the tuples, say A0, A1, and so on, AN minus 1. It is some arbitrary tuple, and I want a function. I want a function f such that phi of f equals this very tuple. But can we define such a function? So its value at 0 is what?
A0.
Of course, what else? Its value at 1 is A1, and so on. So, of course, then, with this definition, f of phi of f equals this set, this tuple, that is, it equals our given tuple. Is it clear?
Yes.
So, now we know that we have a bijection between functions and tuples. It seems trivial, but in fact, that's quite useful. Any questions here? So, if you have no questions, let's move on. Our next topic is so-called embedding. So we know that, excuse me, just wait a little. So, up to now, we know that two sets are called equivalent if and only if there is a bijection. There exists some bijection f from A to B. And informally, that means that that is the intended meaning, the meaning we want to ascribe to this notion. Informally, that means that A and B have the same number of elements, So, but is it possible to compare our sets in such a way that one set has no more elements than any others than other set? So this means that they have the same value of elements. But is it possible to say formally that one set has no more elements as the other one? Of course it is. In order to do that, we will employ injections. So, what do we have? A and B, while there is an injection from A to B. That means that the image of A under our injection the image of A under our injection is then equivalent to A. Is it clear?
Yes.
Because it is an injection and it should be surjective to be a bijection, and it is surjective but for its image. Of course, every function, every relation is surjective for its image. So this function is surjective. So here we have a copy. Here we have a copy of A in B. And this is, in fact, the right notion for comparing our sets. So we say that by definition, A is embeddable. A is embeddable into B if and only if there exists an injection from A to B. So we will use the following symbols. A, F embeds A into B. That means that F is an injection. F is an injection from A to B. And for embeddable, we write this symbol without specifying F. So there is some injection from A to B. It is embeddable. It is possible to embed it. Is it clear?
Yes.
So A is embeddable into B if there is an injection. Okay. Now let's see some elementary properties of this relation. Lemma 1. Every set is embeddable to itself. Why is it so? What is an injection from A to A?
Identity.
The identity function, of course. If A is embeddable into B and B is embeddable into C, then A is embeddable into C. So, which injection should I take here? If here we have F and G here.
G of F.
The composition.
Yeah.
Of course, because the composition of injections is an injection. We know that quite well. If there is a bijection, then there is an injection. And also, for the opposite direction, if there is a bijection, there are two injections. Why is it so? If we have some bijection F here, which injection can we take from A to B?
F.
F, of course, as every bijection is an injection. And from B to A?
The converse of
The converse relation, as it is also bijection and, of course, an injection. And the last one, if A is embeddable into B, there exists some C, which is a subset of B, and it is equivalent to A. C is equivalent to A. And vice versa. If there is such a subset, then, of course, A is embeddable into B. Okay. Why is it so? Let's check it. Let's check it. First, assume that A is indeed embeddable into B. What one can take as C? So there is an injection from A to B. What should one take as C?
The range of F.
The range of F, or the image of A under F, which is the same in this case. So, of course, this is a subset of B, and on the other hand, this image is equivalent to A, and F is the equivalence. Is it clear?
Yeah.
And for the other direction, so assume that indeed there is some C such that there is a bijection F from A to C. But of course, that means that F is a function from A to C. C is a subset of B. Of course, that means that A is a function from A to B. It is not necessarily bijective, but it is still injective, because being injective is a property of our relation itself. It is not relative to any set. It is either injective or not. Either it glues some two distinct points together or it doesn't. Is it clear?
Yes.
So, of course, you may consider F as a function from A to B while it is still injective. And then also a little but very useful remark. If A is a subset of B, then it's necessary that A is embeddable into B. Can you explicitly, of course, that follows from our statements from the first one, but can you explicitly name this embedding, this injection from a subset to the whole set? Excuse me, A and B. What should I take as an embedding? It's very easy. It's trivial.
Wow.
I embedded to himself.
So?
I embedded to A.
So you want to embed A into B. So you need an injection from A to B. Which one can you take?
Identity.
Of course, surely the identity relation. The identity relation is a function from A to A, but as A is a subset of B, then it's also is a function from A to B. And of course, it is injective. So if it is a subset, then it is embeddable. Is it clear?
Yes.
So, and now, let's consider the following question. If A is equivalent to B, then it is embeddable into B and vice versa. But is it true the following? So, question. Is it true that if A is embeddable into B and B is embeddable into A, then A is equivalent to B? Is that true or false? What do you think? If you have two injections, so that means that A, by the way, informally, what does it mean that A is embeddable into B? That means that A is not greater than B. So A has no more elements. So what does it mean that A has no more elements than B and B has no more elements than A? Of course, intuitively, it is expected that they have the same number of elements. What do you think? Would it be natural or expectable?
Yes.
And in fact, this holds. So yes, that's true. But it is not that easy to prove this theorem, which is known as Cantor-Schroeder, German, Schroeder-Bernstein Theorem, or simply CSB. Cantor-Schroeder-Bernstein Theorem that says exactly that. If A is embeddable into B and B is embeddable into A, then that's necessary that there is a bijection between A and B. So if two sets are mutually embeddable, they are equivalent. I won't prove it. For the proof uses some advanced technique, or maybe not that advanced, but anyway, that might be quite hard to understand. It's a kind of limit. Like in calculus, you have limits, so you must construct some kind of limit. But it is worth noting that this proof does not require the axiom of choice or something like that. So in general, it is quite easy. So we shall take this without a proof. But now let's learn how to use this theorem. It is very important and very practical in the following field when you want to prove that two sets are equivalent. It is much easier to construct two injections than one bijection. But first of all, let's apply it to some known facts. We know that no set A is equivalent to its power set. Do you remember this?
Yes.
By the way, is it always the case that A is embeddable into the set of its subsets? So is A less or equal than the set of its subsets?
Yes.
So please, how is it possible to embed some set to the set of all its subsets? So you have to map every element of A to a subset and do it injectively, so that distinct elements will be mapped into distinct subsets. How is it possible to do so?
F of X is the singletons of S.
The singleton of X, surely, that's it. Of course, it is an injection. Why is it so? Because if f of x equals f of y, that means that two singletons are equal. But what does it mean that two singletons are equal? Two sets are equal if and only if they have the same elements. So x is an element of the singleton, so it should be an element of y, of the singleton of y. So that means that x is an element of the singleton, but y is the only element of the singleton. So x equals y. Is it clear?
Yes.
Of course, every element has its personal subset. For example, the singleton. Or another idea is to take the complement of the singleton. That's also possible. So that means that there are at least that many subsets as there are elements. Ha! And what can you derive from these two statements? You know, they are not equivalent, yet A is embeddable into the power set. What does it mean? In view of Cantor-Schroeder-Bernstein Theorem, they are not equivalent, so the conclusion is false. That means that at least one of the assumptions is false as well. But A is embeddable into the power set of A. What does it mean? Dear students, so please. If A is embeddable to B and B is embeddable to A, then they are equivalent. So if they are not equivalent, then what does it mean? Then either A is not embeddable to B or B is not embeddable to A.
The power set Y is not embeddable to A.
Of course, the power set is not embeddable. There is no injection from the power set to the set A. And of course, this is equivalent via so-called axiom of choice. It should be directly proved that this is the same as our statement, which we have actually proved, that there is no surjection from A to P of A, to the power set of A. And of course, for the other direction, that means that there is no injection from the power set of A to A. Is it clear?
Yes.
So, and now let's consider various examples. Example 1. Let's consider these sets: rationals, integers, and naturals. Whether any of these, any two of these sets are equivalent to each other. What do you think? Is any of this set equivalent to any other set?
Yes.
So which one?
R and N and Z.
A and Z are equivalent. We have proved it explicitly by providing a bijection. But what about Q? What about Q, the set of all rationals? Is it countable? By the way, let's give some definition. A is countable. A is countable by definition if and only if A is equivalent to the set of all naturals. So is Q countable, the set of all rational numbers? It is countable. Let's prove it, but without providing any explicit bijection. So N is a subset of Z. Do you agree? Every natural is integer.
Yes.
Every integer is rational. Do you agree?
Yes.
But that means that N is embeddable into Z and Z is embeddable into Q. Do you agree?
Yes.
Yeah.
But why Q is embeddable into A? Let's demonstrate it. That will be very easy. Ha! By the way, what do you know about rationals? Rationals are ratios. So they are quotients. They are M over N. Do you agree?
Yes.
So, for every Q, there exists a pair of natural numbers such that our Q is either plus or minus M over N. Do you agree?
Yes.
But is this pair unique?
No.
Why?
For
Why
example,
isn't it unique? Say 1 over 3 equals what?
2 over 6.
2 over 6 or 3 over 9 or so on. But can we choose just one such pair? Which one can we prefer?
1 over 3.
Why?
It's not reducible.
So, do you know the notion of an irreducible fraction? Irreducible. Irreducible means that its numerator and denominator are co-prime. Have you had the notion co-prime in your number theory course?
Yes.
Okay, so let's take these numbers to be co-prime. So there exists a unique. Did you have such symbol? There exists unique.
Yes.
So there exists unique such pair where A and N are co-prime. And now we shall define some function f, which will be a function from rationals to triplets of naturals. And it will be defined the following way. F of q will be the pair of 0, m, and n. If q is m over n and m and n are co-prime. And what if it is minus m and n? Then it will be 1 mn. And what about 0? Let 0 be what about 0? Let's encode 0 the following way. Is it clear? Is this function clear?
Yes.
Is it injective? Of course it is. If m and n are the same, of course the fractions are the same. Is it clear? Of course, if m equals m prime and n equals n prime, then m over n equals m prime over n prime. So this is an injection. Is it clear?
Yes.
So we don't want to be frugal. We reserve a natural number for the sign. And of course, we don't use every pair of naturals. In fact, we skip any pair where our m and n are not co-prime. Say it is not possible to obtain 2 and 6 here via f. So 0 to 6 is not a value of f. It is not a value of f. Is it clear why? We map every rational to its irreducible representation. Is it clear?
Yes.
So dear students, we have that rationals are embeddable into triplets of naturals. So, but these triplets are just n squared multiplied by n. Is it clear?
Yes.
If they are equal, they are of course equivalent. And this one is equivalent to this one. Why? N squared is
Equivalent to n.
equivalent to n. We know it already. And this is the same. Ha! And of course, if it is equivalent, then it is embeddable. So I see that embedding is transitive. You know that if A is embeddable to B and B is embeddable into C, then A is embeddable into C. So what do I have? I have that N is embeddable into Z, Z is embeddable into Q, and Q, as I can see, is embeddable into N. What does it mean?
Q equivalent to n.
What if I apply my CBS theorem that says that if A is embeddable into B and B is embeddable into A, then they are equivalent. Q is embeddable into N is embeddable into Q. That means that Q and N are equivalent. And what about Z? Z is embeddable into N and N is embeddable into Z. So in general, overall, that means that N, Z, and Q are all equivalent. Is it clear?
Yes.
Okay. And now, let's consider the next example. What about reals? What about reals? What can you say about reals? Say, what is R squared, the plane, the set of all plane points? How many points does the plane have? What can you say about it? First of all, we need some fact. I won't prove it, but it follows. It follows from the definition of reals. There are as many reals as there are sequences of zeros and ones, as there are functions from naturals to zeros and ones. Do you know this fact from your calculus course? Do you know that? Dear students?
No.
So, please remember that. There are as many reals as there are sequences of naturals, sequences of zeros and ones. So these are functions from naturals to zeros and ones. So every such function is a sequence. So f of 0, f of 1, f of 2, and so on. This is just the sequence of zeros and ones. And of course, this set is equivalent. We know that already. It is equivalent to the power set of naturals. So there are as many reals as there are subsets of naturals. That's fundamental. Please memorize it. Is it clear?
Yes.
And now I'll have a magic inequality from which I'll conclude a plenty of interesting facts. First of all, do you agree that this set is equivalent to this one? What is this set? That's what? Describe it. So please, describe it in plain English. This is a set of
Pair
of all pairs where the first coordinate is what?
a real number.
Some arbitrary real number at the second coordinate
0.
is 0. Okay. How many such pairs do you have? Of course, as many as we have real numbers. Is it clear?
Yes.
You may map every pair to its first coordinate, and that will be a bijection. Okay. These two are equivalent. Hence, this one is embeddable into this one. Okay, but is 0 a real number? Is 0 a real number? Dear student,
Yes, this is zero.
of course. So this is the subset of the set of all pairs of reals. In the plane we have this set here, where y equals 0. Here it is, this line. Is it clear? X is whatever and y is 0.
Yes.
So it is a subset of the plane. If it is a subset, it is embeddable. But what is the plane? We know that R is equivalent to this set, but that means that the product is equivalent to this product. Is it clear?
Yes.
Dear students, what do we know about this set? A to the power c multiplied to b to the power c. We have proved something about it, something very interesting.
C powered by 8 times B.
A times b to the power c. So this is just 2 multiplied by 2 to the power n. What is 2 multiplied by 2?
Four.
It is 4, of course, and it is still 4 in set theory. Why is it so? Easy. 2 multiplied by 2 is the set of all pairs. So please name them all. Name these pairs.
Maybe you will come.
0, 0,
0, 0, what else?
0, 1, 1,
What
0,
else?
1, 1.
1, 1. How many of them do you have?
To make 4.
4, of course. Of course, 4. So you have a 1-to-1 correspondence between these pairs and the first 4 natural numbers. And the first 4 natural numbers. So we have a bijection here. Is it clear?
Yes.
And we know that if A is equivalent to B, then A to power C is equivalent to B to power C. We have proved that last time, we know it. So, this is 4 to the power n. But what is 4 to the power n? 4 to the power n is a set of all functions where from? From naturals to
To 4 on the line.
2, 4. So it is a set of all sequences of the following form. Say 0, 1, 1, 2, 3, 0, 3, 1, 0, 0, 2, 1, and so on. All sequences of all infinite sequences of numbers from 4 underlined. So this is a set of all such functions. But every such function, every function from naturals to 4 is a function from naturals to naturals, isn't it? Dear students, is it a function from naturals to naturals?
Yes.
So this is a subset of this set. But is a function from naturals to naturals a function from naturals to reals? Of course it is, because every natural is a real number. So it is included into this set, the set of all functions from naturals to reals. Is it clear?
Yes.
And now my favorite trick. R is equivalent to 2 to the power n. So this thing is equivalent to 2 to the power n to the power n. What do we know about this thing? A to the power b to the power c is equivalent to
B for C.
Is B times C?
a to the power b times c. Do you agree?
C times B?
This is the same.
Oh.
This is the same. You know that b times c is equivalent to c times b. So they're the same.
Yes. Yes.
That is equivalent. So this is equivalent to 2 underlined to the power n times n. But what is n times n? It is equivalent to the set of pairs of naturals. What is it? Pairs of naturals. Dear students,
N quadrant.
that is just n. N squared is equivalent to n. We have proved it. So that means that this set, this one, is equivalent to which one? To 2 to the power n. That is just the set of all reals. Ha! What do I have here? What do I have here? Interesting. I have that reals are embeddable into square of reals, which is embeddable into n to the power n, which is embeddable to r to the power n, which is embeddable to r. So I have the following. Reals are embeddable into reals times reals, which is embeddable to the set of all sequences of naturals, which is embeddable to the set of all sequences of reals, which is embeddable to R. What does it mean? According to Cantor-Bernstein Theorem, Cantor-Schroeder-Bernstein Theorem, what does it mean? Dear students, don't sleep, please.
These sets are equivalent.
Of course, these sets are pairwise equivalent. So we have as many points in the plane as we have points in the line. So the line is equivalent to the plane. It is quite interesting, but that's an inevitable consequence of our axioms. That means that the line has as many points as the plane. It's quite surprising, but that's a fact. Any questions, please? And as our last point, let's talk about so-called continuum hypothesis. Continuum hypothesis. What is it? Ha! We know that reals, the set of reals is equivalent to the set of all subsets of naturals. But this set is strictly greater. It is strictly greater than the set of all naturals. So naturals are embeddable to the set of all subsets of naturals, which is equivalent to the set of reals. So naturals are embeddable into reals, yet reals are not embeddable into naturals. So we may write it the following way. N is strictly less than R. So strictly less by cardinality, by the number of elements, so-called cardinality. So it's strictly less by cardinality. So it has strictly less elements than R. There is an injection from N to R, but not vice versa. Ha! But is there any intermediate set? Does there exist such X which has strictly greater number of elements than N does, and which is strictly less than the set of all reals? Is there such an intermediate X? What do you think?
Rationals or irrationals?
Rationals? Oh, that's a shame. Rationals are equivalent to naturals. They have the same number of elements. But something which is strictly greater. Or an equivalent question. If X is somewhere in between N and R, does it follow from here that X is either equivalent to N or equivalent to R? Or is it possible for X to be somewhere in between? What do you think about that? By the way, this set is called the continuum. The continuum. Why is it called the continuum? For it is a cognate. It is a cognate to the word continuous. Continuous. So the line is continuous, and the set of all points is called the continuum. And of course, this title can be ascribed to the set of all subsets of naturals as well. So is there any set in between naturals and the power set of naturals? Between naturals, between the countable set and the continuum, is there any in-between set? In fact, no question, no answer to this question follows from the axioms. So we have the following continuum hypothesis, CH, or the continuum hypothesis. The continuum hypothesis, it is a statement which is independent from our axioms. The continuum hypothesis says that there is no such intermediate X. For every X, if X is greater or equal or equivalent to N, but is less or equivalent to reals, then it is either countable or it is continuum. So this statement is not a theorem. Please pay attention to this fact. It is not a theorem. But which is most interesting here, the negation of this statement is not a theorem either. So our axioms are fundamentally incomplete. So from our axioms, it doesn't follow that this continuum hypothesis holds. But it's also it doesn't follow that the continuum hypothesis fails. Of course, this is under the condition that our axioms are not contradictory. So we have some statement which we cannot prove and we cannot refute. That's very interesting. Of course, one can have the following question. Why just don't add this statement as an axiom? But which statement do we choose as axioms? The statements must be intuitively true. We should like them, but consensually, mathematicians don't like this continuum hypothesis enough. Mathematicians don't like it enough. They don't think that it should be intuitively true. So they don't take it as an axiom. While it has been proved that it is not possible to prove it from other axioms, nor it is possible to refute it. That means that it is somewhat undetermined, and you cannot use this continuum hypothesis in your proofs, nor can you use its negation. Is it clear?
Yes, yes.
So we have a very easy question without any easy answer, without any answer possible from our axioms. And of course, all this stuff results in a deep philosophical question. Whether this statement is true in principle, and what can you think about it in general? If you take line, a continuous line, you should have some intuition of that line. If you pretend to be a mathematician of any kind, and you have an intuition of naturals on this line, but what about that in-between set? So, any questions, please?